Hello everyone, welcome to my YouTube channel Civil Sphere Insights. In this video, I will discuss some important MCQ for fluid mechanics. Previously, I have discussed 10 questions for fluid mechanics. Now in this video, I will continue from the 11th question. Also, I have discussed some important MCQ for strength of materials, RCC design, steel design. So if you have not watched them, you can watch by clicking the links given in the description box. If you have any recommendation, please let me know in the comment section. And please, and one request, this is a newly created channel, so please support me by sharing and subscribing to get more such videos. So let us start with the 11th question. So which of the following relationship is correct? So the question is asking about relationship between the various types of pressure. So let us understand the types of pressure first. So first of all, we have our atmospheric pressure. Okay, so what is our atmospheric pressure? This is the pressure that is exerting by the atmosphere, right? So this atmospheric pressure at mean sea level, MSL, is called our standard atmospheric pressure. Okay, standard atmospheric pressure. Okay, and the atmospheric pressure other than in sea level is called local atmospheric pressure. Okay, it is the pressure other than mean sea level. So whatever we are measuring pressure except our mean sea level, if we are measuring atmospheric pressure, then it will be called as local atmospheric pressure. Okay, so now we have our gas pressure. So gas pressure is the pressure above atmospheric pressure. Okay, above atmospheric pressure or below atmospheric pressure, that is our gas pressure. When the pressure is above atmospheric pressure, we call it as gas pressure. When it is below when the pressure is below atmospheric pressure, then we call it as negative gas pressure. That is also called as vacuum pressure or suction pressure. Okay, now we have absolute pressure. So absolute pressure is nothing but the summation of atmospheric pressure plus gas pressure. Okay, so if I want to represent this pressure by the line diagram, then suppose this is our zero pressure, absolute zero pressure. This is our atmospheric pressure, and above atmospheric pressure we have our gas pressure. Okay, below atmospheric pressure we have also gas pressure, right? But that is negative gas pressure. Okay, at this point. Okay, so this is called vacuum pressure, right? Okay, so if I want to calculate pressure at this point, then we call it as P absolute. Okay, P absolute. And also at this level we also call it as P absolute, right? Why? Because this is the atmospheric pressure, right? At this level we have our atmospheric pressure, right? P atmospheric, right? So above this, so P atmospheric, at the up to this level we have P atmospheric, right? And if I add this gas pressure, then we have P absolute. Okay, P absolute is nothing but the summation of atmospheric pressure plus gas pressure. And at this level, up to this level, if I want to calculate the pressure at this point, then we also call it as P absolute. Why? Because it is the summation of here atmospheric pressure minus this, right? That minus this gas pressure, right? So it is minus, right? So P atmospheric pressure minus P gas is equal P atmospheric, right? Okay, so now what is the correct answer? So absolute pressure minus atmospheric pressure minus gas pressure. So if I deduct atmospheric pressure and gas pressure from absolute pressure, so let us assume this absolute pressure, let us take this absolute pressure. So if I deduct atmospheric pressure from this level. So we'll have this was our absolute pressure, right? This was our absolute pressure. So deducting atmospheric pressure, this thing, right? This portion is deducting. We have now our P gas pressure, right? So then we deduct gas pressure. So we'll have nothing, that is 0, right? So the answer is our option A. Let's go to the next question. So an equilateral triangular plate of side is immersed in water with one side at free at the surface. The center of pressure is below the water surface at a depth of. So in the question there is a equilateral triangle. There is an equilateral triangle which is touching the free water surface. Okay. So this is touching the free water surface, right? So here it is our triangle. We need to find the center of pressure, right? So this is our center of pressure. Suppose this is our H and dash, and this is our centroid of the plate, which is denoted by X bar, from the top of the water surface. Okay. So now we know the formula, that is for vertical plate we have the formula, that is our X bar plus moment of inertia of centroid upon Ax bar, right? So now we need to find one thing for calculating moment of inertia, right? That is our H, vertical height, right? So for calculating that, do something. Let us. So this is our A. In the given question, we have side measurement as A. This will be A, right? This base is A. So if I take this portion, then we have A upon 2, right? So if I want to apply here Pythagoras theorem, so this height H will be under root of A square upon 4, right? So finally we have A root 2 upon root 3, right? Root 3 upon 2, right? So now if I want to calculate center pressure, so here X bar is equal H by 3, right? From the base we have H by 3, right? And if I want to calculate from apex, then we will have twice H upon 3. But in this case we are referring our top surface, free water surface, so we'll have H upon 3, right? Plus I of G. So I about G will be BH cube upon 36, right? And here A X bar, here A is BH upon 2, right? Into X bar, that is our H by 3. So here A square is cancelled by A square. Now we have H at the top. Now B is cancelled by B. So these are 6. So if I cancel out this 6, here will be 6, right? So now finally we have H upon 3 plus here H upon 6, right? So finally we have H by 2, right? So but we need to find in terms of A, right? So our formula will be H by 2, right? So here H, the value of H is equal A root 3 upon 2 upon 2, right? Upon 2. So that is our A root 3 upon 4. Okay. The answer is A root 3 upon 4. Okay. Now coming to the next question. A floating body will remain in stable equilibrium if the metacenter. So let us do a floating body. Suppose this is our water surface. Here it is our body, solid body, which is floating, right? So here in this case, depth of immersion is more than the non-depth immersion, right? So now our center of buoyancy will lie below the center of gravity, because here depth of immersion is more. Okay, so a center of gravity will be lying above B, right? So if I give a angular displacement to this plate, this vertical plate in the clockwise direction, then the scenario will be something like this. This will be tilted in this way. These are initial axis, right? These are vertical. This is our G, right? This is our B, right? Okay. Now in this case, since the volume displacement is changed, because when you are giving angular displacement to this body, this floating body, the volume of water displaced is also changed, right? So here the volume of water displaced is also changed. So the buoyancy will also be changed, right? So our new buoyancy, suppose here, be this, okay? So if I want to extend this line, so it will intersect somewhat here, okay? This will be our meta center, right? So this is our new buoyancy, right? So this is our buoyant force FB, and this is our weight, right? So in this case, we have this is our FB, right? So initially we give a tiltation in anti-clockwise direction to disturb this stability, right? If it can come to its original position, then it will be in stable equilibrium, right? So if it doesn't come to its original position, then it will be in unstable equilibrium. But in this case, the disturbing moment that we produce in the clockwise direction, these are disturbing moment, right? These are disturbing moment, right? So disturbing moment was given in the clockwise direction, but here a moment that is generated, that is in the anti-clockwise direction. You see that this will be moving this way, and this will tend to rotate the body anti-clockwise, right? So it will resist the moment. It will resist the disturbing moment, right? So this resisting moment will sufficiently produce. Will be sufficiently produced to disturb destroy this moment, and finally the body will be in initial position. That is called our stable equilibrium, right? So when our meta center is above our gravity center of gravity, then the body will be in stable equilibrium. But if the condition is something like meta center is below the center of gravity, suppose our meta center is here and our gravity is here, okay? So in this case, our weight will be acting downwards, and meta center, so which bound force will acting upwards, right? So in this case, our moment will also be, our resisting moment will also be in the clockwise direction, okay? So it will not help the body to come in its original position, right? So the body will be in unstable equilibrium because the moment cannot be destroyed in this case, right? So the answer is our above the center of gravity, okay? So meta center will always be above the center of gravity, right? So the next question, a line along which the velocity potential is constant is known as, so velocity potential is constant, that line is called as equipotential line, right? Let us assume a steam tube. Steam tube means a series of steam line, okay? These are series steam line. Suppose these are steam line along which the flow is occurring. So we know that across the steam line flow is not possible, right? So this is our across. So in this direction, flow is not occurring, right? So why flow is not occurring here? We know one thing, that flow always possible from high pressure to low pressure, right? From high pressure to low pressure. Suppose this is there will be some pressure, right? And there will be also some pressure. So there is high pressure and there will be low pressure. For that, the flow is occurring, right? So consider this line. So in this line, flow is not occurring along this line. Why? Because along this line, at every point, the pressure is same. That's why flow is not occurring along this line, okay? So this is called our equipotential line. So this is our equipotential line. Always remember that along equipotential line, flow is not possible, okay? So let us move to the next question. In order to measure the flow with a venturimeter, it is installed in, so we know that venturimeter can be installed in anywhere, in anywhere. It doesn't affect the discharge. So we can install it according to our convenience. So answer is any direction and any location. So fancimeter is a discharge or flow measuring device that is a very accurate. It gives very accurate result, and also it is very costly. So now the next question is stipulative wire is trapezoidal wire having side slopes, not slide, that is a typing mistake, side slopes. The stipulative wire is nothing but a trapezoidal wire. When you provide 1:4 1 horizontal to 4 vertical slope to a wire, this is our trapezoidal, right? So if this is a wire, so if I provide a 1 horizontal to 4 vertical, then this will be called as stipulative wire, right? Okay. So why we are providing this slope, this particular slope? The problem is that when you are providing a rectangular wire, in this case, chances of eddy losses and contraction is more, right? So due to this, some discharge is lost, right? So to avoid this, we provide 1:4 slope, so that our eddy losses and contraction are minimized. Okay. And one thing, if a question is asked, what is the slope? What is the slope in theta? So that slope will be 1/4, right? 10 theta. 10 theta by 2 is equal to 1/4. So theta is equal to nearly 28 degree. Okay. So the answer is our theta is 1:4 degree. Theta is 28 degree, right? To 4 horizontal. 1 horizontal to 4 vertical. Okay. The divergent cone angle in a fanciometer is generally kept lesser than the convergent angle. So we know that our divergent, there are two sections in a fanciometer. The diverging is done very at a higher rate, faster rate, but converging is done at very lower rate. Okay, why such that? Why? The reason behind this is because these are diverging, no? These are diverging, right? Diverging. This is our third portion, right? And this is our converging, right? So if this angle is nearly this angle, diverging angle is 23 degree, around 23 degree, and this converging angle is our 4 to 7 degree. Okay. So if I provide here a more angle, if I expand this line, this section to here, so what will happen? Flow will since the flow when flow will be occurring here. Now finally suddenly this area is reduced, right? So here velocity will be what? V on A2 V2, right? So if area is reduced, velocity will be more, right? So in this case velocity will be more. Okay. So if the velocity is more, then what will happen? The water will pass at a higher rate, right? A large chances of flow separation will be there. Okay, water will pass this way, right? It will not passing this side. Okay, so this portion is our useless. So it is called flow separation. Okay, so here will be generated ED. Okay, here will be generated ED. Okay, so it means that if I expand this line, if I provide a greater angle at conversion section, right? This is our not conversion, this is our diversion, right? So if I provide a greater angle at the diversion section, then our discharge will be lost, right? Our discharge will be lost. So in order to avoid that, we provide at a range 4 to 6 or 4 to 7 degree. Okay, so we provide 4 to 7 degree angle. But in this case, in our conversion section, there will be no chance for flow separation. Okay, flow separation is not dominant in this case, but in this case flow separation is dominant. Okay, so to take care of this, we provide 4 to 7 degree of divergent angle, right? So to avoid separation of flow. Okay. So coming to the next question, if the friction factor of the laminar flow through a circular pipe is 0.1, Reynolds number will be, so there is a formula for from Darcy's friction factor, that is our F is equal 64 upon RE. So here what is given here, friction factor value is given 0.1, so 64 upon RE. So we need to find RE, right? So RE equal 64 upon 0.1, that is our 640. Okay, the answer is 640. So dimension of Sage's coefficient here. So there is a formula for from Sage's velocity. V is equal to C under root of RS, right? So here the C is called Sage's coefficient. So we need to find the dimension for Sage's constant. So there is a formula for C, that is our 8G upon F, right? If I want to determine dimension from here, then these are unit. This is our unitless. These are constant, so no dimension. These are unitless, so no dimension. So we have only G, right? So G means acceleration due to gravity. So LT inverse 2 under root, right? That is our L raised to power half T raised to power 1, right? So L raised to power half T raised to power minus 1. Okay. So coming to the next question. If n is the Manning's rugosity coefficient and r is the hydraulic radius, the equation of Sage's constancy is, there are two equations for expressing velocity, Manning equation and Sage's equation, right? V is equal to C Rs and V is equal to 1 by n r raised to power 2 by 3 s raised to power half, right? If I equate these two equations, then we will have in terms of C, right? We need to find in terms of C. So C is equal to be, so Vc is under root of Rs equal 1 by n r raised to power 2 upon 3 s raised to power half. So s raised to power half is cancelled by s raised to power half. Now we have in terms of C, right? C is equal 1 upon n r raised to power 2 upon 3. So this under root of r gone to this side. So we have half. So 1 upon n r raised to power 1 upon 6, right? So the answer is 1 upon n r raised to power 1 by 6. Okay. So let us move to the next question, our final question, that is, for most economical section using Sage's formula of flow for maximum discharge, the circular channel of the diameter d is, if you derive expression for maximum discharge by using Sage's formula, then in terms of d you will get this value. This is our 0.95 of d. So if the section is 0.95 of the diameter of the section, circular section, then it will give maximum discharge. So we have come to an end. So this is for today. So thank you for watching.